In January 2021, security researcher Jan Masters discovered that Peloton's backend API had no authentication requirement. Any request to the endpoint returned user data, age, gender, city, weight, workout statistics, regardless of whether the account had been set to private, regardless of whether the requester had any relationship to the account holder, regardless of whether the requester had a Peloton account at all. The privacy setting users had configured was enforced correctly in the mobile application. The API that delivered the same data did not check it. Peloton's initial response was to add authentication. The endpoint now required a Peloton account to call. Any Peloton member could still access any other Peloton user's private data. The fix had addressed the wrong problem. Authentication confirms who is making a request. Authorization determines whether that specific identity is allowed to access that specific resource. Peloton had enforced the first and not the second. Every authenticated user's request was now confirmed as coming from a real account. Whether that account had any right to the data it was requesting was never checked. The data remained accessible through the API to the full membership base until TechCrunch contacted the company in May 2021, and the vulnerability received public attention. A privacy control that worked correctly, an authentication system that worked correctly, an authorization check that did not exist on the path that mattered. All three facts coexisted because authorization had been applied to the visible presentation layer of the application and not independently enforced at the data layer beneath it. A permission system can be correctly configured, correctly enforced, and completely bypassed if there is a path to the protected resource that does not pass through it. This is the structural logic of partial authorization failure. Authorization is not a property of a resource. It is a check applied at a specific point on a specific path between a requester and what they are requesting. A check on one path does not extend to any other path. A correctly enforced permission model on the primary UI does not protect data accessible through a direct API call that skips that model entirely. Both paths reach the same resource, only one of them was secured. Every resource has an authorization surface, the complete set of paths through which it can be reached. Authorization must be independently verified at every point on that surface. Not once, at the most visible path, but at each path individually. The investment in securing the primary path provides no protection against access through a secondary one. One unprotected path to a resource makes all other protections on that resource irrelevant to an attacker who finds it. Broken access control has been the top-ranked entry in the OWASP Top 10 since 2021. It holds that position not because it is the most technically sophisticated vulnerability class, but because it is the most consistently present. Partial authorization failure is the default output of how authorization is typically implemented. Authorization is added to applications reactively. An endpoint is built. A developer considers whether it needs a permission check. If the endpoint is prominent, handles obvious sensitive operations, or resembles other endpoints that have checks, the check is added. If the endpoint is a batch version of an existing function added for performance, a legacy path carried forward through a migration, an internal utility not originally intended for external access, or a secondary format of data already exposed elsewhere, the check may not be added because nobody specifically stopped to consider it. Three patterns produce this failure consistently across real applications. The first is the Peloton pattern: front-end enforcement without independent back-end enforcement. The presentation layer correctly restricts what users can see. The API endpoints that serve the same data to the same front-end are treated as internal infrastructure and not subjected to the same authorization logic. The security exists at the surface the developer sees. The surface the data actually travels through is unprotected. The second is insecure direct object reference. A user is authenticated and authorized to access their own record at an endpoint that accepts an identifier. The permission check confirms the user is authenticated and holds the right to access resources of that type. It does not confirm that this user owns this specific identifier. Changing the identifier in the request returns another user's record. The authorization system answered the right question at the wrong scope. It verified the user can access records, not that this user can access this record. The gap between those two questions is where the failure lives. The third is endpoint proliferation without authorization governance. In September 2022, a threat actor accessed an Optus API endpoint that was publicly reachable without any authentication. The endpoint had been built for authenticated third-party developer access. It had been left exposed in the production environment without that authentication requirement applied. The attacker sent requests with sequential customer identifiers and extracted data on 9.8 million Australians. The main Optus API was correctly secured. This one path was not. The protection on every other path did not extend to this one. Each of these patterns produces the same outcome. The authorization model covers the endpoints someone thought to secure. It does not cover the complete authorization surface of the application. The uncovered paths are not visible in the permission model. The permission system reports correctly configured endpoints as correctly configured. The unprotected paths are outside the model entirely. The asymmetry matters. Securing 10 paths into a resource does not reduce the risk from an 11th unsecured path. Authorization is not cumulative across paths. Each path either independently enforces the authorization requirement or it does not. The absence of an authorization check on any single path is sufficient for that path to be exploited, regardless of how thoroughly every other path was secured. The question that applies to any application is not whether authorization checks exist. They do, on the paths someone was thinking about when they built the check. The question is whether the complete authorization surface has been mapped, every path through which each resource can be reached, and whether each point on that surface has been independently verified to enforce the same authorization logic. In most applications, that mapping has never been done. The authorization surface that was considered and the authorization surface that exists are different things. The gap between them is where access happens without permission, without any entry in the permission system being wrong, and without any of it appearing in the logs as a violation.